All right, so the first thing I'm going to go over is I'm going to go over PES diagram and how to read these. So when you go to read a PES diagram, the way you want to look at it is this. Look at the energy, the ionization energy at the bottom of the graph. You're looking for the highest value. The highest value is going to be, the highest ionization energy is the electrons that are closest to the nucleus to remove. Close to the nucleus they are, the harder they are to remove. See how this is 100, then it goes 10, then it goes 5. That tells me the first hill automatically, I know that's going to be 1s right there, 1s2. The next hill automatically is going to be 2s because I know that, 2s2. This is going to be 2p. That would make that, the next one that comes is 3s, and then finally 3p. So I label that. The first thing I look at is the energy values. It asks me what element does the spectra represent? Well, remember the relative height of the number of electrons is related to the height. So the height of this, we know that there's 2 electrons there, which means the height of that is going to be 2 electrons there when for the same energy level. So the 2 here, if I divide that into thirds, I know that's basically 2p6. And then I get here, this is 1s, right? So there's 1s there, and then 3p. When I look at 3p, it basically has to be 2 electrons. If you look right there, because it's about double the size. So that's about double the size of that. So it's going to be 3s2, and then actually that would be 2. So 3s3, 3s2, 3p3 would be that, because this represents 2. 3s2 is full here. It's a little slightly higher. So half that basically would mean that that would be equal to 3p3. So ultimately, that's how I know it's the element phosphorus. So you have to compare the relative heights to each of the ones in the energy level here. Which peak represents the 2s subshell? Well, the first one we know, the highest energy level, or the highest amount of energy is going to be related to the first energy level, which is going to be 1s2. So the second hill has to be represented. So the peak at 6.84 megajoules per mole would be your answer choice for that one. 3. An electron from which peak would have the most Coulombic potential energy? Well, Coulombic attraction is two things, Coulomb's law, right? Q1 times Q2, charge and distance. It's related directly to charge, inversely to distance. What that means is the closer the distance, the greater the charge. So in this case, that's going to have the greatest Coulombic attraction. So the correct answer is A, the peak at 104 megajoules per mole is going to have the greatest Coulombic attraction. That's what you're looking for. Number 4, how many valence electrons does this atom have? Well, when you go to find valence electrons, it's the outermost level. So when I look back at this chart, clean this off here, this was basically 1s here. This is 2s, 2p, this is 3s, and then this is 3p. That's the highest level. We already know 3p holds 2 electrons. This is slightly higher. The height, relative height, means it's got to be 3 because it's not double that. Double would be like there for 4, which means I tell the number of valence electrons from the outermost or the lowest energy value, because I know the closest energy value would be 1s. All right, next one. Why does an ion of phosphorus, P3, have a larger radius than a neutral atom of phosphorus? Think about it this way. If you're P3, you get the charge 3 minus from the fact that you gained 3 electrons. Normally, a phosphorus atom without a charge, its atomic number is 15, which means it has 15 protons, means it also has 15 electrons in the outside of the cloud. Coulombic attraction works both ways, or Coulombic repulsion. So when you talk about electrons in P3, the greater the number of electrons you have, the greater the repulsion, because there's a natural repulsion. That's why electron clouds get bigger. When you add electrons, the more negative something becomes, the larger it's going to be, is because you're increasing the Coulombic repulsion between the electrons. More electrons, basically more repulsion between each other as far as atomic size. It's referring to atomic size in that case. Number 6 I'll do in class tomorrow. We'll skip that. Which neutral atom of the following elements would have the most unpaired electrons? Remember, when you go to do unpaired electrons, what you do is you look at basically the last two subshells. You fill in the last two subshells. So the correct answer is manganese. So why is it manganese? Why would it have the most? Well, if you look zinc, you should know zinc is at the end of it. Zinc is 4s2, 3d10. But those are paired. Those electrons are all the way paired. So when we look at manganese, when you go to write out manganese, the electron configuration for manganese should be 4s2, 3d5 is manganese. So when I go to do this is a horrible drawing, but you get the idea. I basically have to put 5 electrons in the D range. So I got 1, 2, 3, 4, 5. Remember Hund's rule, the electrons don't pair up until there's 1 in each energy level, giving it 5 unpaired electrons, making it the largest number of unpaired electrons. Nickel, I believe, is 4s2, 3d8, right? So there's 8 electrons, but when I go and fill in nickel, I put 3 more in here to get to 8. It really only has 2 unpaired electrons. So when you need to figure out unpaired electrons for an electron configuration, you need to do basically the last 2 subshells check, especially if it's a D atom. Next one. Which element will have the higher electronegativity value, chlorine or bromine, and why? Well, basically, bromine, the electronegativity value, the easier it is to attract electrons is, again, talks about Coulombic effect, is you're basically going to be, the smaller your radius, the tighter you're going to be able to pull electrons in a bond. So like fluorine is extremely small. If you look at the flag rule we use for periodic trends, here's the periodic table right here, sort of drawn like this. Remember the flag for radius is over here. Here's the flag for radius. So when we talk about ionization energy, the ionization energy is directly related to size. Electronegativity is related to size as well, because the smaller you are, the closer you can pull the electrons in a bond. So the smaller it is compared to bromine, because chlorine's here on the periodic table, bromine's going to be here, it has a higher electronegativity. 9. Which of the following elements has the highest energy subshell completely full of electrons? So if we look, the correct answer is zinc. If we go sodium, sodium is 1s2, 2s2, 2p6, 3s1. There's only 1 electron in the outer shell of sodium. Aluminum is the same idea as 1s2, 2s2, 2p6, 3s2, 3p1. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So if you notice in its outer subshell or outer layer, it has 7 valence electrons. When we go to write the electron configuration for zinc, the last line is going to be 4s2, 3d10, and then if you notice there, its highest energy sublevel is completely full. Why is zinc completely full? Because if you think about it like this, when you go to write an electron configuration, when you go to do it by energy level, like to remove electrons when it ionizes, you do it in order energy level first. So this would be 3s2, 3p6, 4s2, 3d10. Remember, the outside level 4 is a higher level than 3d, so I pull it over here. 4s2, its highest energy level is completely full. That's why zinc is the correct answer for that one. Which of the following isoelectronic species? Remember, isoelectronic means the same number of electrons, has the smallest radius. The way it works is the more protons you have, the more greater the Coulombic attraction. So Coulombic attraction, positive and negative particles will always pull towards each other. So the other way to remember is this: the more positive you are, more positive means smaller. When you talk about ions, the more negative, larger. If we look, they're all isoelectronic. Sulfur on the periodic table normally has 16 protons, 16 electrons. When it becomes S2 minus, it gains 2 electrons, 18 electrons. Chlorine normally has 17 protons and 17 electrons, but a negative 1 charge means it goes to 18. Same thing with this one. Argon has 18, doesn't have a charge. Potassium normally has 19 electrons, but when it gets a plus 1 charge from losing an electron, it goes to 18. All of these are isoelectronic. So when I have to decide who's larger or who's smaller, what do? Well, if I'm looking for the smallest radius, I'm looking for the most positive one. Most positive one automatically means it's going to be K+. Will automatically be smaller because it has a greater Coulombic attraction. the largest one is going to be S2 minus because it's gained 2 electrons, and so the electrons will repulse each other. Plus, it has a lower number, a lower Coulombic attraction because it only has 16 protons in its nucleus. 11. What is the most likely configuration for a sodium ion? Keep in mind when you read this, there's a difference between an ion. Oh, it says a sodium ion in its ground state. So it's a sodium ion, which means it has a charge, which means it's Na+. So it's a noble gas configuration. So sodium normally is 1s2, 2s2, 2p6, 3s1. That's a normal electron configuration for sodium. When it ionizes the positive charge, it loses that electron. So when it loses, it's an ion, but it's in its ground state. You still have to adjust the number of electrons. It just means that last electron hasn't been elevated or kicked up. So the correct answer is going to be B. So if it says an ion, what does that mean? Ion means that you have to remove whatever the electrons are based on the charge where it is in the periodic table. 12. Which of the following statements is true regarding sodium and chlorine? Well, sodium is here on the periodic table, crude drawing. Chlorine is over here. And they're asking me, remember trends of the periodic table. The major trends you have to know are radius. The flag for radius would be down here. That's a horrible drawing. Ionization energy and electronegativity would be here. So when you basically, this should have been really easy. So chlorine should be closer here, or chlorine is closer here, which means it has a higher electronegativity. It also has a higher ionization energy. It's going to be smaller though. Sodium would be larger based on where it is in the periodic table, but the correct answer is D. Chlorine has a greater electronegativity and a larger first ionization energy. Remember, ionization energy is directly related to size. Smaller the atom, the harder it is to remove the electrons. Atom of silicon in its ground state is subjected to a frequency of light, causes an electron ejection. The electron from which subshell would have the highest kinetic energy after ejection? Okay, so the amount of energy that's basically going to be provided, the amount of kinetic energy, means they're asking for least binding energy. The amount of energy that basically attracts an electron to a nucleus, the Coulombic effect, is greatest for 1s2. Why? Because it's the closest to the nucleus. So as you go this direction, the amount of binding energy, or the amount of energy that basically holds the electron in, is lower. So that means when you hit it with some electricity or a charge, electromagnetic light, and you bump this electron out, since this is held looser, it's easier, you're going to have greater kinetic energy. So what's going to happen is, since this is more loosely held, when you hit it with a beam of light, this electron is going to just break off at a greater rate because it requires less energy to bump it out, where this electron, which is very, very close to the nucleus, has a much greater binding energy. You saw like the amount of binding energy on that chart we looked at earlier. Will have a lot slower kinetic energy because most of the force went to knocking it out. 14. Wavelength range for electromagnetic radiation. While ultraviolet is this. Which type of radiation has more energy and why? Remember, we talked about this, is the teeter-totter of light. So if you look at it like this, you have radio waves here. It goes red. Monkeys in Virginia use extra gum. So radio waves are the biggest. As you go this direction, energy and frequency get greater because what happens is wavelength and frequency are inversely related to each other. So the longer a wavelength that a wave has, the less frequency it has. And as you go from radio waves to microwaves to infrared to visible light, the energy is increasing and so is the frequency, but the wavelength is decreasing. So ultraviolet has a higher frequency compared to infrared. So if you look, ultraviolet's here, infrared's there. Next one, which of the following nuclei has 3 more neutrons than protons? Well, remember when we're going through and doing these, the way it works is isotope notation. What you do is you typically will list the symbol of an atom, the mass number, which means the number of protons and neutrons. Because remember, if we're doing this, if we take a look at it, the upper number, we say all the mass of an atom is located in its nuclei. So like here, if you have boron here, boron has a mass number of 11. That's all of its protons and its neutrons. So then what happens is we take its atomic number, which is 5, subtract it, we get 6. So we have, when we subtract the two of them, that basically means I have 6, or actually I subtract it here. 11 minus 5, I'm going to get 6 neutrons. So when it asks you have 3 more neutrons than protons. Then I do chlorine. Chlorine has 37 for our mass number. That's protons and neutrons. Its atomic number is 17. Subtract that, I end up with 20. Well, I have 23 more neutrons than I have protons. That's the difference between them. That's why B is the correct answer. 16. Which of the following ions has the smallest ionic radius? Remember, the way it works is the more positive you're going to get. More positive means smaller when you're talking about ions. They're also, these are all isoelectronic, right? If you look here, they're all isoelectronic. So this means that has 10 electrons, that has 10 electrons, 10 electrons, 10 electrons. So size is going to be dictated by effective nuclear charge. So effective nuclear charge is going to control the Coulombic effect. The one that has the most protons, and aluminum with 13 protons in the nucleus, is going to suck those 10 electrons greater. So the more positive an ion is, the smaller it's going to be. 17. Which of the following is true of the halogens when comparing them to other elements in the same period? Their electronegativity is higher than other elements within their period. So remember, electronegativity, the most electronegative element in the periodic table, this is a horrible drawing, is actually fluorine, supposed to be over here. Fluorine, will move it over. Whoops. Move fluorine over there, is the most electronegative, and then francium would be the least electronegative. So just remember general trends of the periodic table. In general, do metals or nonmetals from the same period have higher ionization energies? Nonmetals. The reason why nonmetals, because as you go in the periodic table, if you look here, another crude periodic table drawing, sort of, well, like this. Remember, ionization energy is directly related to size. So as we go this way across a period from left to right, and the nonmetals are on this side of the periodic table, the number of protons in the nucleus is increasing, but making the size of the atom smaller, making the electron harder to remove. So if you have filled a complete energy level, or they're closer to having a filled complete energy level, is basically increasing the ionization energy, but that's not the best explanation. On the AP exam, they're going to ask you for who has the greater effective nuclear charge. 19. Ionization energies for an element are listed below on the table. How do you figure out which one is the element? Well, remember, the trick is you look for when you see a jump in energy. So if I had electrons and I'm removing electrons, let's say I'm setting up the different atoms here, right? So if I look here, I have core atoms. It asks me like magnesium, for example, sodium. Sodium only has 1 electron in its outer core. When it removes it, you should see the jump in ionization energy from the first level to the second level. It's got to basically triple. In this case, it doesn't even double. So we're looking for a big jump, because that's when you're removing inner core electrons. The inner core electrons are closer to the nucleus here. So the closer they are to the nucleus, the harder they are to remove, because greater Coulombic attraction. So sodium's jump, it can't be sodium because there's not more than a triple jump, or right around a triple jump. So then we check magnesium. Well, magnesium has 2 valence electrons. So if you're an element that has 2 valence electrons, the first valence electron comes off. It takes 11, whatever that is, volts or whatever. The second one is 15. When I go to grab the third one, notice the third one is 80. See the spike where it spikes energy right there, going from 15 to 80 is a spike. That's how I know that it represents an element with 2 valence electrons. Same thing with this one. A researcher listed the first 5 ionization energies for a silicon atom. So when we look at a silicon atom, think about it like this. When you look at the number of valence electrons in silicon, it has 5 valence electrons. That represents a silicon atom, right? So when you're going to pull these off, the first one, energy, the second one, the energy increases. Third one, the energy increases. Fourth one, the energy increases. But when you go into the inner core, when you go to remove an electron from the inner core, that's where you're going to see your spike. So if it has 4 valence electrons, the 5th electron removed is where you would see the jump. So if you look here, the jump here, this jumps in the first one, so it can't be A. This one basically doubles, those not so much. I'm looking for one where it basically skyrockets. So look at D. First one doubles, second one doubles, third one less than doubles. The fourth one, it goes from 4,000 roughly to 16,000. That's how I know that would represent the ionization energies for silicon, because whenever you see a spike in energy, that tells you that you are grabbing core electrons which are closer to the nucleus, and they're harder to remove because of a greater Coulombic effect. All right, hope this helps. I'll see you in class tomorrow.